Okay, there are more scenarios. So we take a look at that in a bit. But what I want you guys to do, okay, we have completed page 22, go back to 21. We will now understand, right, why in secondary school they always tell you that salts are neutral. It's just this salt is neutral, honestly. Okay, so the first reason is that sodium plus has a low charge density. Later we will see how this is relevant. The second thing I need you all to take note of is Cl minus. Can someone tell me who is Cl minus partner? Good. Cl minus the partner is HCl. HCl is an acid. Cl minus is the what? Conjugate base. Okay, before I proceed, can I ask you another question? Does Na plus have a partner? Who? Wrong. There's no partner. Is NaOH and Na plus a partner? Okay, I'm going to use the word partner from now on. Don't use that in the exam. But I'm referring to the term conjugate acid-base pair. Do they differ by only one H plus? No. They differ by OH minus. No such thing. We never learned that before. So don't tell me that they are partners. Right? That's why we don't use this explanation. Okay, HCl is obviously a strong acid. By comparison, Cl minus is a weak conjugate base. Guys, if you see the word weak, right, do you think this salt can undergo a reaction with water? No. Okay, that's why there's nothing. That's why it doesn't undergo hydrolysis at all. Okay, so Cl minus is a weak conjugate base of HCl. Thus, Cl minus cannot react with water. Okay, that's why there's no hydrolysis. That's pretty much it. I never really see questions, right, testing you guys salt like that. Okay, they have better things to test. Okay, so this one really it's just for your own information to know why the salt doesn't produce any H plus nor OH minus. Okay, so it's not neutral because your school said so last time. Okay, it's neutral because it doesn't hydrolyze. That is the new thing that we've just learned. Okay, I'm gonna delete this one. Okay, this one not very important. Okay, instead, I need you all to take a look at the next page. Page 23, I think. Okay, we're going to look at another equation, similar, right? So I'm going to have a weak base, NH3, reacting with an acid HCl to form NH4 plus and Cl minus. Okay, can you all identify a partner? A pair, a conjugate acid-base pair? Okay, good. The NH3 is a weak base. NH4 plus is a strong conjugate acid in comparison. Again, it's not as strong as something like HCl. It's still considered weak if you look at it objectively. It's just stronger than this. Okay. Okay, we deal with this first. Guys, if this salt here, again, now guys, these two constitute the salt. But we look at the left ion first. Can this guy react with water? Can he react further with water? There's a big fat strong over there, right? Okay, so you can react with water. In this case, you just tell me NH4 plus. Now it's an acid. So it's a stronger acid than water. So this is how you justify that it can undergo hydrolysis. Yeah. Yeah, correct. Pretty much like most of your questions. Because they won't test on a weak like scenario like just now, the first scenario. Okay, but just to show you guys. Again, guys, the important part here is to give me a salt hydrolysis equation because we have now verified that it can indeed undergo hydrolysis. Again, this equation is the most important because they always test. You need to craft it out yourself. So guys, what do we do? The salt in this case in question is NH4 plus. What does it react with? Water. What arrow do we use? Reversible. And what do we form? NH2. 3. Okay, I heard wrongly. Okay, so NH3, because that's the partner of NH4 plus, right? They can never be separated. Okay, and then to balance this out, what do we have? H3O plus, which is your so guys, the salt is Acidic, basic, or neutral? Acidic. Let's box up the H plus. Okay, this means, okay, let's just add it on. Since the concentration of H plus is more than the OH minus in the solution, the salt or the solution is acidic. Your pH less than 7. So this challenges the idea that you have learned in secondary school. Salts don't have to be neutral. Salts can be acidic as well. Why? That's the equation that you understand. Okay? So if you haven't seen the relevance for this first point, it is stronger than water. That's why you can force the position of equilibrium to the right. You can see that. This one dominates over water, proceeds the equation to the right hand side to produce H plus. Imagine if this guy was weak instead. Do you think he's powerful enough to force the reaction to the right? No, that's why the reaction doesn't proceed if this was a weak species. But he's strong enough, so you can force it to the right. Does that make sense? Okay, so strength is kind of like to force the position of equilibrium to the right. Can see these two scenarios. These are two scenarios in which the salt can undergo a further reaction with water to produce either H plus or OH minus. Any questions? No? We'll look at the third scenario. So far, we have taken a look at salts, right? Now we're going to look at the metal ion. And what I need you all to do, turn over to page 24. That's the last scenario for salt hydrolysis. Guys, again, the word salt is used very loosely. Salts can constitute two different ions. Sometimes the ion can be a metal, like Na+, or it can be any other metal, right? So what we're going to do is this. I erase the bottom one. I need you all to draw in a small little diagram in school. Help you understand. You see the equation at the start? This is an odd equation. It looks very weird. AlCl3 somehow can react with 6 water molecules to produce this thing here. And I think now to highlight this ion on the back. What the hell is this? Okay, so this thing over here is the hydrated metal ion. In other words, guys, Al3 plus can be surrounded by 6 water molecules. You may have a lot of questions right now. Why are there 6 water molecules? Why not 5? Why not 4? Okay, this one, right, has to do with the idea of complex ions. Right now, you all don't know much about that. So I can't answer you all on why it is 6. Just accept it as 6 first. Eventually, the answer will be reviewed in like the last topic of training. Look at this guy first. As you can see, these two guys constitute the salt. You can see that? They are just a salt in general. Okay, I know this doesn't look like a generic acid-base reaction. Okay, you bear with me first. What we are concerned with, okay, can Cl minus react with water? And we established that at the first example, right? This guy is a weak conjugate base. Don't care about him. Okay, but let's look at this guy instead. Okay, before you write down any salt hydrolysis equations, let's do this. Okay. I want you all to draw a diagram. This diagram here looks like that. Al3 plus is surrounded by 6 water molecules via dative bonds. Guys, why are there dative bonds? Who is giving the dative bond? Okay, obviously it's water, right? But which part of water allows it to give this dative bond? Okay, it is oxygen which contains a lone pair. So I need you all to draw the diagram with oxygen bonded to the aluminium. Okay, the water on the right hand side, right? I'm going to draw the bonds. In the rest, just draw normal water. Make sure the O is bonded to the native. Okay, so you've never really seen something like this before. But basically, this is a complex ion. Complex ions have its own definition and whatnot. Okay, but that's just how it looks like. It looks weird, it looks complex, right? Okay, guys, you all remember just now, I mentioned Na+. Can Na+ undergo hydrolysis with water? Answer was no, but why? We only mentioned one thing. It is very low one. Yes, okay, it has a very low charge density and somehow it doesn't do hydrolysis. Why? Right now, Al3 plus has, in comparison, high charge density. And this will allow it to undergo hydrolysis. So you look at the reason first. Because it is such high charge density, it has very high polarizing power. In other words, you can think of it this way. This Al3 plus is super attractive. Electrons love it. Very attractive, right? Okay, it will polarize what? Who does he polarize? Who is around him? Who is surrounding his ass? H2O. Okay, just look at one H2O. It will polarize the what of water? Just polarize water. You can only polarize what? Electron clouds. So imagine this outline over here represents the electron cloud of water. So imagine what's happening here. All the electrons of water are super attracted to the Al3 plus because this guy is very attractive. Right, so everyone's like flocking towards this guy. Where all the electrons are gravitating towards the middle. What do you think will happen to this bond over here? Okay, all the electrons from here moving towards the center. What happens to the bond? Stronger or weaker? It will be weakened over time because the electrons are all gone, right? Then what will happen? Eventually, what will happen? It will break. And when you break already, what happens to the H? Comes out as H plus. So the solution is acidic. Okay, so this is how the polarization process works. I'll write down the explanation one more time. But I need you all to come up with an equation first. As you all can see, Al surrounded by 6 water molecules must react with what? The salt must react with water, correct? Reversible equation. Now guys, how many water molecules do I have left in the diagram? I am only left with 5 water molecules, right? What happened to the 6 water molecule? It became OH. Can I ask you all what's the overall charge in this case? Overall charge. This one overall charge is +3. This one is okay, +2 because OH is OH minus, right? So this is 2 plus. And how do you balance this out? Okay, look at what it produced. It produces H plus, right? Or in other words, H3O plus. Can see what's happening first? Okay, so bear in mind, I repeat in simple terms. Al3 plus, super attractive. Electrons are all flocking towards the center. As a result, the bond here starts to weaken. Eventually, it breaks to produce H plus. The entire process, I'm going to write it in words now. So first, it all starts off because Al3 plus has high charge density and hence high polarizing power. These two words come hand in hand. Polarize what? Polarize the electron cloud of water. Okay, always ask yourself what's the next step. We just talked about polarizing. You must tell the examiner what you polarize. Polarizes the electron cloud of water, which will weaken the covalent bonds. The OH bonds to be particular. So guys, just now sodium plus, right? He's too unattractive already. He's too weak, too low charge density. So no one wants to be attracted to him in the middle, right? Then none of this will happen lah. Can see that? Okay, that's why sodium plus, our explanation was very simple. If you have low charge density, it doesn't result in anything else. So my explanation stops there. Okay? By this case, it weakens the OH bonds, eventually breaks. And when the OH bond eventually breaks, you release H plus. And that's where you get an acidic solution, and I need you all to memorize the pH of this. Some of you guys may have done periodic table, the chapter in school already, okay, which also contains this exact explanation. You need to memorize it as pH. I'll highlight keywords, and I need you all to always look through these keywords to memorize. Okay. Now, one thing is a lot of people will write the word weaken but forget to write the word break, which defeats the entire purpose of the question. You can weaken the bonds all you want, but if it doesn't break, it won't produce H plus. Then none of it will make sense. Okay. So I know again right now, I want to bring you guys back to the overall theme of this chapter. We are still undergoing salt hydrolysis. This right here is a metal cation. Sometimes metal cations can appear in a salt. Like for example, Na plus, sodium plus, right? So because all these ions can appear in salts, we still have to account for its possibility of undergoing hydrolysis. It's a bit different from what we went through just now. Okay, but it's still part of a salt, possible. Can you see that so far? Yeah, so those are all the scenarios we'll cover. We'll do a practice right now. Can you all take a look at page 25? Okay, after we finish salt hydrolysis, the segment, right? We'll take a break. Okay. Now, can you all take a look at page 25? The first, okay, there are two questions there, right? And I'm sure you all can recognize that both of them are salts. But to make your life a bit easier, I'm going to show you guys the origins of each salt, and I need you all to write it down. Okay, what do I mean by that? Okay, how do you form KBr? KBr is formed via HBr and KOH. So you form KBr, water. Okay, what is this question trying to ask you to do? Okay, I want you to try out. This is obviously the salt, and the salt is made up of two ions. You need to check each ion whether they get hydrolyzed or not. K plus, Br minus. What's the explanation for each ion? Can they hydrolyze? The second question, okay, as you can see there, CH3NH2 plus HCl to form CH3NH3 plus and Cl minus. Once again, these two guys constitute the salt. You have to check each individual ion to justify whether it can undergo hydrolysis. So you all do that first. Check whether this guy can or cannot. Can or cannot. Okay, I've given you the species at which it originates from already. Okay, so try the first question. Just try part A. Yeah, let me just label the species correctly. Okay, HBr is a strong acid. This guy is a strong base, as you guys should know. Okay, I'm sure you have seen HCl before. Everyone knows that HCl is a strong acid. HBr is in fact a stronger acid than HCl. For a very simple reason, actually, I can show you guys right now. Okay, so from now on, you should know HBr is a very strong acid. It's because, as an acid, they need to break these bonds to dissociate H plus, right? And this bond happens to be weaker. So if HBr is a weaker bond, That means it's easier to dissociate H plus. Okay, that's just for your information. Okay, this is not an explanation to the question or anything. Alright, so I hope you all know from now on, HBr is actually a very, very strong acid. Stronger than HCl. All for the simple reason of bond trap. Okay. But anyways, with that said, right, how do we explain K plus? First of all, can you tell me, can K plus undergo hydrolysis? Answer is no. It's a metal ion. Metal ions, in order to undergo hydrolysis, it must have high charge density. Does that look high to you? Okay, no. Okay, so K plus out. Okay, how about Br minus? How do we explain Br minus? Are you going to tell me it's low charge density? Is that the relevant explanation? Okay, no. How do you explain Br minus? Okay, good. It has a partner, does it? Right? It has a partner over here, HBr. So if this is a strong acid, Br minus is A. Okay, in comparison, it's a weak conjugate base. Can that be a reporter in the first place? No, you can't force any reaction forward. It's weak. So that's the answer to this question. Okay, so K plus has low charge density, unable to undergo hydrolysis. Next, Br minus is a weaker base than water. So it can't force any reaction forwards, right? So you can just go straight to telling me, thus it cannot undergo hydrolysis. Finally, let's do a conclusion. So guys, this salt is acidic, basic, or neutral. Both ions in the salt cannot undergo hydrolysis. So the pH here is 7. This is the secondary school acid-base equation. Strong acid, strong base, come out, right? You get a neutral salt. This is what we've been all used to last time. But the next question is what you guys are learning right now. And the more relevant question is actually part B. So I need you all to give this a try. Okay? Few minutes. Okay, try to write the explanation also. You guys may not know, okay, but maybe you guess this first. Right? Once you identify this species, right, the rest of the question you should be able to do. Okay, can someone tell me CH3NH2? What is this? Conjugate, it should be on the usually on the right hand side. Okay, we identify acid or base first. This is ethyl base. It's base because this is obviously an acid. Everyone knows HCl is a strong acid. So this is a base, but is it weak or strong? Okay, anytime you see the NH2, that kind, right, it's always weak. Okay, so that is the species first. Okay, once you know this, right, you can try the rest. Okay, tell me whether the each salt can undergo hydrolysis first. If can, right, I need you all to come up with an equation also. The salt hydrolysis equation for this. Okay. Okay. All right, perhaps we justify the Cl minus first. Okay, can this guy undergo hydrolysis? No. Okay, you don't want to write an explanation for this, it's fine. Okay, it's not like you write it much anyway. Okay, so Cl minus is going to be a weak conjugate base compared to the strong acid. So it's not even going to react with water. However, this is a weak base, giving you a strong conjugate base, strong conjugate acid in return. Now, once again, don't be fooled by the word stronger. It's not like you'll be on par with like HCl. He's just stronger than this guy. Okay, this is very important because that caused a bit of confusion in the other class. Right? So I have to really clarify this. So first, you tell me CH3Na3 plus is a stronger acid than water. Now, why am I not writing the word conjugate if you're wondering? Again, the word conjugate, right? It just means he's partnered with this guy. Now, you don't have to tell me whether he has partnered or not, right? Okay, objectively, he's just a stronger acid compared to water. So you can skip the word conjugate. Okay, so thus it can undergo hydrolysis. Okay, since it can hydrolyze, I need you all to check your salt hydrolysis equation. Hey guys, what's the equation here? Okay, first you take the salt, CH3NH3 plus. You react with what? Okay, water, what's the arrow? Reversible, what do you form? Okay, good. CH3NH2 is partner. Again, you don't know, just look at the original fraction. Okay, plus 1. Okay, H3O plus, because you see the left hand side plus charge, right hand side should have a plus charge also, which can only come in the form of water. Sorry, H3O plus. Okay, so because of that, let's come up with a justification. This overall salt is good. Right now, you have a bit more H plus than OH minus ions in the solution. So the salt is acidic. pH less than 7. So as of right now, this question here is like a model question, right, of what you will see in your exam. They will ask you guys to come up with an equation and determine the pH, probably for 1 or 2 marks. Okay, and then the next segment we're going to go to is calculations, which is honestly not that difficult because we did the same thing in the last lesson. Okay, so hydrolysis calculations only come in more importantly in the next lesson. Okay, but now we just look at a few basics first. Okay. We're going to do page 27 and 28, then we'll take a break. Right, just 2 short questions. Okay, guys. Any questions? Don't have. I'll bring you guys through question 1 together on page 27. Okay, read through that question first. It's like 1 sentence, right? Okay, very nice. They ask us to calculate the pH of CH3CO2 minus Na+. Okay, CH3CO2 minus Na+. This is a salt. Can we all agree on that first? Okay, so you see a salt, guys. Immediately you all think of salt hydrolysis. What else? Right? Okay, so salt hydrolysis, which salt? Which part of the salt? The whole thing? Okay, which part can undergo hydrolysis right now? Okay, only the CH3CO2 minus. I don't want to see Na plus in your equation. Okay, I know some of you put it in because, oh, spectator ion. No, here I do not want to see Na plus in your equation because it does not hydrolyze. I'm trying to write the salt hydrolysis equation. So guys, please take note. All our calculations in this topic, the very first thing I need you all to always write down is the equation. Number 1 thing, if I don't see an equation, you're not going to calculate properly anyway. Okay, not going to work. Okay, cultivate this habit. And this equation, I need you all to write it down yourself in a bit. I list down the other steps first. The second step here is to come up with we're going to use this equation. Okay, for a very good reason later. And then an ICE table. Okay, let me tell you guys what to do first. In this question, I need you all to come up with the equation and just put an ICE table underneath. That's it. Okay, don't need to do the second step yet. Okay, everything will come in. Okay, salt hydrolysis equation, most important. If you can't craft this equation, right, you're going to struggle in this topic. Okay, that's why it's very, very important. Okay. The arrow is wrong. Okay. Okay, nice. Very good. If you want to fill out the table, you can go ahead and try also. Okay, we're going to fill out the ICE table. Okay, but very nice. Okay, the salt in question is CH3CO2 minus, reacting with water, and must see reversible. Later we will see when to use full arrows. It's very easy. Okay. The partner is CH3CO2H obviously, and OH minus. Can see that so far? Now, before we do any calculations, can I ask you all from a qualitative perspective? Your answer at the end of the day, the pH, will it be more than 7 or less than 7? Or equal 7? Okay, more than 7, right? Because now you can tell that's OH minus. That's one way you can check your answer. Later you calculate 1 less than 7, you know it's wrong already. Next, IC table. Guys, can you tell me what's the initial concentration of the salt? Did they tell us? Okay, good. They will tell us, right? 0.1. Okay, do we care about water? No, never care about this guy. Okay, so initially you haven't undergone any hydrolysis, so the right hand side must be 0, obviously. Do we know how much it hydrolyzes? Is it all 0.1? Okay, how do we know only a little bit will hydrolyze? Okay, because reversible. Right? Okay, so we use what's X. Just like the previous lesson on dissociation. Last lesson, it was dissociation of the acid or base. Now is the hydrolysis of the salt. As you can see, they are just different words expressing the same. Okay, so table very easy. Now guys, what do you do with the equilibrium values? Equilibrium values must substitute into the equilibrium constant. Right? What's the equilibrium constant here? We've learned a few, right? Okay, which one do we use? Ka or Kb? Come on, narrow it down for you guys. Ka or Kb? Okay, take a look at this equation. Take a look very closely. A or B? Okay, why do you say B? Good. Okay, there are a few ways to know why you must use Kb for this question. Number one, this is a base, which produces its conjugate acid. Okay, now guys, the word conjugate just indicates that he's a partner. He's partner with the other guy on the other side. Fundamentally, this is a base acid. A base must produce OH minus, right? So very clearly, I must use Kb. Did they give me Kb? Hey, wow, what they give me Ka? What's going on here? I can't do this question, is it? What should I do now? How do I find Kb? It's because of the equation that I've given you on the second step. We have learned that in the previous lesson. So what I need you guys to do now is this. I need you all to find Kb by taking Kw divided by Ka. If you can't remember Kw's value, is in the data booklet, first page. Find the value of Kb first, and then afterwards, you can substitute the values of X into the Kb expression. But can we work our answer using this? What must we do? This is quadratic. What do we do? We approximate it to be x squared over 0.1. Okay, we can do that, right? Because we assume that x is super small. It's way smaller compared to 0.1. So that's how you can get rid of it. Okay, then you can equate this to a Kb. Eventually, I need you guys to solve for x. As for what x represents, okay, that's up to you guys to find. Right? Okay, not very difficult. The only catch in salt hydrolysis is that you need to flip the Ka-Kb. In other words, you just need to look at what they gave you in the question. Okay, don't just flip for the sake of flipping. I'll show you guys that, oh, here OH minus means we'll use Kb. So anyhow, just flip. Now next time you just flip for everything, then you get confused also. Okay. Let's solve for the value of x. They ask yourself, what is x? How does that help me find the pH? Right? to the value of k is 5.56 10 to the power minus 10. Okay, solve for x. X should be, we're going to check. Some of you guys may have forgotten to square root the x. Okay, can someone tell me what x represents in this case? This value. What does it represent? OH minus. Good. Okay, this question wants us to find pH. pH must be, you must find OH minus first, then you can work your way towards pH. Okay, but how do you work your way towards pH? What's the next step right after this? Okay, pOH first. After you find pOH, then you find what? How? Good. 14 minus pOH, we get pH. That's the final answer. Okay, and you should get 8.87. Once you're done, right, you can just proceed to the next question because it's the same exact thing, right? Okay, next question, just try yourself. Okay, this is full answer. Okay, good. Now over here, salt hydrolysis seems fine. It looks very similar to dissociation. Okay, but when titration curves come in, right, you must be able to spot when salt hydrolysis happens. That's the additional feature on top of the calculations. Okay, then you need to see where it happens, then you can apply the correct technique. Okay, so that one, right, the next lesson requires us to be well versed in today's lesson. If not, can't proceed. It's always linked up. Okay, so far, any questions? Anyone cannot get this answer? If okay, right, we shall take a break first. Okay, since just nice we are 1 hour in. Okay, later we're going to do buffer, which is the most hefty portion. We are not going to, I don't think we can finish buffer by today. There'll be a little bit left, but it's fine. Okay, take a break first. We should now wake up. You're gonna call her, wake up, right? Okay, come, let's continue. Right. Okay, so we're gonna do buffers now. Similar idea as just now. Okay. This is probably the portion that most people struggle with. Okay, so let me clarify from the start. What is a buffer? Okay, so guys, a buffer solution, right, has one purpose: to resist pH change when you try to change it. Okay, so let's look at the full definition. A buffer solution is a solution that resists pH changes, okay, upon addition of, okay, upon adding small amounts of acids or bases. This definition need to memorize because it will be tested. Again, it's not something that you need to hardcore memorize, right? I mean, it's quite self-explanatory. Buffer in English means to protect yourself against something, to resist against something, right? Okay, so you're trying to resist. Don't use the word prevent. Prevent is more absolute and it's wrong. Because a buffer is not a magical solution that will always resist pH change. If you add large amounts of H plus or OH minus, obviously it's going to destroy the buffer, right? It's like buffer is like protection, but this protection is not foolproof. So if you put too much H plus or OH minus, it will eventually spoil the buffer. So it's only small amounts. Okay, so keep in mind first. Okay, next, we're gonna understand at the bottom of page 29, what is a buffer actually? How to prepare a buffer, right? How does a buffer resist pH change in the first place? Okay, let's just put that question at the back of our heads first. Okay, you can think about it. What does it do to the H plus or OH minus, right? First of all, you must understand a buffer contains an acid conjugate base pair. So guys, I ask you a question. How many species are there in a buffer? Based on this information. Two log is a pair, right? A buffer must contain two species, both differing only by one H plus. That's the definition of conjugate pair, right? That's what we discussed. So once again, just to make sure we're on the same page, they differ only by one H plus, nothing else. That is if you put both of them in the same solution, right, they can actually resist pH. And just based on this information alone, can you look at the options of page 29? Can you guys tell me what are the possible answers here? What are the possible ways to form buffers? Okay, let's look at option A. Can option A form a buffer? Okay, guys, first of all, right, I need you all to take note, remove the Na plus. Because Na plus is just a spectator ion. I don't care about spectator ions. So if you rewrite option A, right, you look something like this. HCO3 minus and CO3 minus. Can you see that? So can or not? Can, right? Okay, solid. Option B, can or not? CH3CO2H and NaCl. Possible to form a buffer. Do they differ by one H plus? Not at all. They differ completely. They're different completely. Right? Okay, out. No. That one we'll touch on it later. Because NaCl is a neutral salt, we won't react. You can see that. Not NaOH. I think you confuse with NaOH. We'll cover that later. Okay, so right now the species, let's assume none of them will react first. We start with the base level. Guys, cannot tell me option C. I got rid of Na plus once again. I don't care about it. You care about it. Okay, first of all, does it fulfill the conjugate acid base pair? It does, right? But this one doesn't actually form a buffer also. Because a buffer must also have another criteria. It must only contain weak species. You can bear this in mind. No strong species allowed. HNO3 is a classic strong acid. You can't have anything strong in a buffer. So it is quite aligned with the theme of this chapter. This chapter talks about weak species most of the time. So your buffers need weak stuff also. Okay, can? So two criteria lah, only weak stuff. Okay, bear this in mind. This one really important for the next portion. Okay, so how do you prepare a buffer? Okay, so you look at the next page, page 30. The first two methods are very, very obvious. You can just mix an acid and a conjugate base, put them in the same container, settle already. Okay, write down examples. Acid conjugate base pair, most common example is our favorite ethanoic acid. Just go and find these two guys and then just throw them into the same solution. Finish. Is there a reaction here? Are they going to react? No lah, they are partners of each other, right? Partners of each other just stay like that, can already. Okay? Next, you can also mix a base and its conjugate acid. Most common example will be ammonia and NH4+. Again, there's no reaction here. You just mix them together, they'll just swim around the solution. So let's give these guys a name. This is like a direct method. Why is it a direct method? Because you are literally just mixing them together. Is this difficult? No. Okay, you're just mixing. What I'm really concerned with, right, is the third method over here. The title of this third method is called partial neutralization. Okay, we will look at this later. Okay, we'll look at the name in a bit, but right now I just need you all to imagine this scenario. Okay, so finish up the first two. Okay. Okay, so if you want to pay attention to this page, it will be the third portion. Let me present to you guys a problem. The problem is sometimes I do not have both the acid and conjugate base at my disposal. In real life, sometimes I only have CH3CO2H. Meaning if I want to make a buffer only of this one guy, I need to have something that can produce this guy also. So this is the indirect method where I'm producing both species on the spot. Does that make sense? Okay, compared to the first two methods, I have one container of this, one container of this, so I just mix them together. But sometimes, in real life, I only have one of the two species. So now I need to generate the other guy at the same time, simultaneously. Okay, what should I do? Okay, CH3CO2H, I only have this guy, right? Can someone tell me how do I generate the other guy? What do I add? This is an acid. How do I form its conjugate base? Acid must react with a base lah. Okay, so let's just write OH minus. Let's just assume this is the strong base, right? Okay, let me put NaOH just to clear up any confusion. Okay, let me just put NaOH. A very strong base, as we all know. Because when the acid and the base reacts, I will form my conjugate acid. Sorry, conjugate base, which is right here. Now guys, which two species am I interested in? For my buffer to operate, I need this guy, the acid, and this guy, is conjugate base. Can you see that? So what I'm doing in this portion here is that I only have an acid and I only have NaOH. But when you react both of them together, I can form his partner on the spot. But the issue is, how much NaOH do I need to add? So with this, right, I need you all to write down an ICF table. Just a table to showcase different values. First of all, the first example I'm going to go through, I need you guys to write text. Because we're going to erase this. So look at this now, guys. Imagine I have 1 mole of CH3CO2H. We're going to look at a few scenarios. How much NaOH do I add? Okay, at the start, I do not have any conjugate base. I can see this is the problem I've been telling you guys about. I don't have the other guy. Now, the question is how much NaOH should I add? If we're not sure, let's try things out. Okay, why not? Since this is a very nice 1-to-1 mole ratio, let's just add another 1 mole as well. Okay, so that they will completely react. Okay, now this one don't really need to write first. Okay, you can take a look. Of course, all will react, right? So you -1, -1, right hand side will +1, right? Look at the final values. Final, right, means after the reaction is complete. Look at the values at the bottom. Can I form a buffer? As we mentioned, we need 2 species, right? But right now I only have the conjugate base. That one doesn't form any buffer. That one is just a salt. Agree? So this is clearly wrong. I can't put 1. Okay, now the question is, should I put more than 1 or less than 1? Let's try more than 1. Okay, so why not? 1.2. Okay, if I put 1.2 NaOH, 1.2 moles, what happens? Okay, good. You get 1.0 because this is the limiting reagent. So -1, -1, +1. Okay, math it up. Can this form my buffer? Why cannot? Okay, first of all, I don't even have the pair. And I have what? What's this? This is a strong base. Can I have anything strong inside? No, look at the rules. Must only contain weak stuff. Okay, so wrong also. I can't put more than 1. What's my only option left? Okay, let's put less than 1. Okay, this one, then we finalize it. Okay, you must put less than the acid. What's the rule for that? Okay, we'll come to it a bit. Let's put 0.6. 0.6 means this is limiting. You minus 0.6 minus the right hand side will be plus. Can see that? Can this form my buffer? Look at the reaction afterwards. I have both the acid and conjugate base. Okay, so I have leftover acid and I have now produced some conjugate base. As long as I have a mixture of both, a buffer is formed. As for how much there is, we don't care about how much yet. I'm just trying to show you guys the rule for this. This is called partial neutralization. I'm sure you can see why now. It's not a one-to-one reaction, it's limiting reaction. In other words, to summarize this up, your strong species must be limited. This is the main thing to remember. If you want to add any strong items, right, it must be limited. Why? Can any strong items remain in the solution? No. I do not want any strong species. So you have to make sure it's limited so that it reaches 0 at the end of the day. You cannot have anything strong, if not the buffer doesn't work. Can see that? Limit your strong species, the weak species is in excess. Okay, just remember what it can be. Can you see that? Okay, so this will have an exercise on the next page, okay, to understand this a bit better. Okay, right? So on this next page, can you all take a look at these values? Okay, just a tip, convert all these values into moles. I mean, it's quite fast anyway, just type the calculator once. Convert all these to moles, and we'll, okay, maybe you'll go over option A, then the rest of the options you'll do yourself. Right? Yeah, erase this direct method. Okay, as you can see, this is the indirect method, which is more common. Okay, I need you guys to pay attention to the indirect method more, because you will see more of this than the direct method. Direct method too easy, they won't test something that easy. Okay, let's look at option A. Let me show you guys what I want you guys to do. Okay, they want you to check which option will give you a buffer solution. The first option is, let me just automatically convert first, 0.025 moles of HCl, 0.005 moles of NH3. Okay. You mix these two guys together, can they form a buffer? Come, we do part A together. Okay, we check both methods, the direct method and the indirect method. Are they both a conjugate acid-base pair immediately? Okay, they're not obviously a pair, but can they react? They can, right? Okay, you have a lot of space to write all this down. Okay, so you can write it at the bottom. Okay, HCl is the strong acid, NH3 is the weak base. What are you supposed to check for? Okay, so guys, this is an MCQ. You don't really have time, right? To get plot everything into 4 different tables. You have 4 options there. Look at the rule here. It's the strong species limiter. It's my strong acid limiting. Yes, that's your answer. That's how you skip all the tables. If you don't believe me, never mind. You can draw the table yourself. You have plenty of time to do it on your time. Right? Okay, go and draw the table. You will notice that the strong acid will end up at 0, and you will have a mixture of NH3 and what? You have a mixture of NH3 and NH4 plus. Okay, without drawing any table, are you all able to predict how much NH3 and how much NH4 plus? Okay. Okay, good. 0.0025 moles of NH3 left over. This for the leftovers, right? And what? Good. You have produced fresh NH4 plus. Newly produced. Okay, you have put it this way. Huh? Go and do all this for the other 4 options. Okay? So this is all about the partial utilization. Okay, annotate. I need you all to annotate. I mean, you're not doing this in the exam anyway. Not yet. This is not exam. This is notes. Okay, so notes. Okay, release now for options B, C, and D. Very, very common question in exam, like super common, like 100% guarantee for test. Okay, go and do all this additional stuff also. Okay, tell me how much of the acid and conjugate base do you actually have after the reaction, right? What doesn't make sense? I'll go through in a bit. Okay, come, let's go over this. Right, let's look at B. Okay, the first thing you should ask yourself is, are you going to get a buffer directly from this? No, okay, there's going to be a reaction first. Okay, can they react? Actually can. NH4 plus acid or base. Okay, it's an acid. Okay, this is a weak acid. Okay, so some of you all might notice already, right? Whenever I say NH3 is a weak base, NH4 plus will be a strong conjugate acid, right? But am I comparing to NH3 in this case? No. So hear me out first. Option B, NH4 plus is just a standalone species. His partner isn't there. So we don't write that strong conjugate acid wrong. Compared to NaOH, this guy we all agree is weak. Yeah, okay. So NaOH is a strong base. We all know that. Objectively speaking, this guy will be much weaker. So that should be our consideration first. Okay, so it shouldn't be like, oh, conjugate, strong conjugate acid. None of that. Okay? Okay, so they will react, yes, but without doing all the table and all that nonsense, right? Okay? Can this guy form a buffer? To check, it is, oh, I erased it. Okay, to check, the strong species must be limiting, which is true. It is limiting, in this case, it will form a buffer already. Okay, but let's add on. What are the species in the after the reaction and how much of it? Okay, what are the species here? Okay, good. 0.0025 left of NH4 plus, right? Because that is after reaction. So this is again leftovers. And then what else do you have now? Yes, okay. This NH4 plus and NaOH will react in order to form NH3, which is its partner. Now then you have the conjugate acid base pair. Now you will have a buffer. It's just floating around. It doesn't matter. Again, sodium is just a spectator ion. It's literally just sitting there. Yeah, okay, can? Okay, next. Option C, can or not? HCl is a strong acid. This is a what? CH3CO2 minus. Okay, we should know it's a base. It's a weak base, objectively speaking. Alright? We are not comparing to its partner here. So don't tell me strong conjugate. Don't use the word conjugate. Because the word conjugate is to tell me that his partner is someone. But no, his partner isn't here. So don't need to use the word conjugate. Okay, so is the strong species limiting? No, right? The strong species is not limiting in this case. You are not going to get a buffer. But again, since let's just expand on this, what are the species you will get after this reaction? Can someone help? Okay, you will get CH3CO2H because that's post reaction. Okay, how much of it? Yes, okay. This is the limiting reagent, so you should get the acid afterwards. But what else do you have? This is in excess, right? So you're gonna have remaining HCl. So you got bracket here. This is leftovers. HCl once again is a strong species, cannot be in the buffer. That's why this is wrong. Okay. Next. Hey guys, take a look at the last one. Tell me what the species here, okay? So we have a strong base and a weak acid in comparison, okay? Okay, they will react because acid plus base, obviously. Okay, and you can see the strong base is limiting, so you form another buffer here. What are the species? 0.0025 moles of. Okay, you get CO2 minus that's newly produced, right? Okay, but then this weak acid, since it's in excess, there will be leftovers of it as well. Now you have an acid conjugate base pair, so it does form a buffer. So that's what the buffer actually looks like. Okay, the second statement. All good? Yeah. So we're not going to look at the calculations yet. Okay, right now we are going to look at how a buffer actually works. So once you're done with this, turn over to page 32. There's a big fat page for you guys to write how a buffer works. Okay, before we go into the actual explanation for the questions, right? Let's understand how a buffer actually operates. So, looking back at the definition, yes, it will not change the pH much when you add H plus or OH minus. Now imagine this. I have a cup of water and I pour a bit of lemon inside. I just throw one slice of lemon. What will happen to the water? It will taste sour, right? It tastes sour because the pH has dropped. Okay, it has become acidic. Okay, sure. But now instead of water, I take a buffer. If I take a cup of buffer and then I pour the same lemon inside, now what would the buffer taste like? Does it taste acidic now? Does it taste sour? No, it will taste the same as before because the job of a buffer is to resist that pH increase. Make sense? But how does it actually do that? Like now we know what's inside a buffer, right? A buffer must contain, let's just say, an acid and its conjugate base, right? You can draw this in also. When you throw in H plus, what must happen to the H plus so that the pH doesn't change much? Can the H plus be swimming inside? It must have disappeared, reacted, right? Reacted by what? Who reacted with the H plus? Who got rid of the H plus? In this particular context, the base. The base gets rid of the H plus. Now, conversely, if I were to throw in OH minus, the pH doesn't change. Why? Well, because what happened to the OH minus? It has been removed by the acid instead. So it can remove both, right? Because you have both species. So what's this reaction called? This one react this one react this. What's this reaction? Base, acid, acid, base. This is a neutralization reaction. In other words, guys, go and note down. A buffer uses neutralization as its fundamental concept. It operates using the concept of neutralization. It doesn't remove H plus using magic. It uses neutralization. And now, before we look at the actual explanation, I need you all to write this down also. When do we use arrows? Full arrows and reversible arrows. Go and write this down. We use a full arrow only for neutralization reactions. On the other hand, we use reversible for anything that's not neutralization. What is not neutralization? There's stuff like hydrolysis. There's stuff like dissociation of uric acid. This is the only rule you should always follow. You ask yourself, do you have an acid and base reacting? If the answer is yes, go and put a full arrow. Don't need things. Meaning in this portion, in this topic here, buffer, I cannot see any half arrows here. The moment I see a half arrow, it is wrong. Buffer uses neutralization, full arrows only. If you're not sure, never mind, just go and check. Do you have neutralization? Yes or no? That's all. Okay? So for this particular question, okay, we're gonna write words now. Okay, so I need I need you all to write equations for this first, okay? Because they always ask you guys with 8 of an equation, they never write here, but must write. Can you all give me the equation where you add H plus? And what happens when you add OH minus? Give me that equation. Who does H plus react with? Who does OH minus react with? Right? Yeah. If I add H plus, it is the drop of CH3CO2 minus to remove it. If I add OH minus, it is the drop of the acid to remove. Here for water also. Okay, give me these two equations, that's 1 mark. The second mark comes in with your explanation. Alright? And the explanation is this. Okay? To remember the explanation here, I need you to remember an analogy. Now guys, how does a buffer actually work? When you add small amounts of H plus and OH minus, why is it that the pH doesn't change much? Now, imagine I take a tablespoon of lime sour and I pour it into the ocean. Is the ocean going to become sour? Why? Okay, because its scale, right, is so small compared to the ocean. So now I need you to transpose that analogy to a buffer. The acid and conjugate base pair is the ocean. Imagine the size, the proportions lah, huh? However much acid or OH minus you add inside is like a tablespoon. Okay, so with that said, I need to see both keywords. The small amounts of H plus or OH minus added is completely removed. It is completely removed by the large excess of acid and conjugate base pair in the buffer. The main keywords here are to really show the scale difference. Small amounts versus large excess. And use the word completely removed to show that it is really the scale difference. And hence, the pH remains relatively constant. Do not ever tell me it remains constant. Because later when you do calculations, there will be a slight change. It's not a magical solution anyway. Okay, it will change a bit. I'll address some other issues, some other questions you guys may have as well. Okay. Can I understand this explanation? Okay, not very long. 1 mark here, 1 mark for the two equations. That's how you can secure the 2 marks. And yeah, okay, common question also. Now, someone may be asking, right? Why must it be an acid and conjugate base pair? I just told you all that and stuff. You all just accepted it. Why can't it be an acid and base, like a normal acid and base? So for example, why must it differ by only 1 H plus? Why can't they be CH3CO2H and NaOH, right? I mean, of course, the most easy way to explain this is that they will react. They will react to form this anyway. But why can't it be any random acid or base? It's because, right, this is how the pH remains relatively constant. Let me show you guys the technical, like, explanation. Okay, you all remember the Ka expression for this guy? It looks something like that. Okay. So the acid conjugate base pair, right? It must be a conjugate pair so that they can both appear in the same Ka. If it is a random acid and base pair, right? They can't be in the same Ka. Why must they be in the Ka? So this is how it works, guys. Okay, look at the first scenario only. When you add H plus, what happens to this species? Increase or decrease? Okay, it will drop by a lot or a bit. How about this one? Increase by a bit. Okay, so you look at the formula now. The CH3CO2 minus drop by a bit. CH3CO2H increase by a bit. Is it going to change much? Basically, it's very minimal, right? Yes, I know it's not constant, but it's very minimal. Ka, is that a constant? Yes, okay, this one is 100% constant. Look at this. If Ka is constant, this ratio is also barely constant. Then H plus must be also like barely constant, correct? So this one doesn't change much. If H plus doesn't change much, pH remains relatively constant. So you can see that. This is the more technical explanation. K is constant, the ratio doesn't change much, so this one also cannot change much. Can? Right? Okay, that's why they have to be a pair, right? In order for all this to work. If it's some random ass acid base, right, you can't even come out with a K. You know, so if you're wondering about that. Okay? Okay, so far. Alright, let's move on to the next page. Page 33, similar scenario. I need you guys to write the same thing out. Okay, I need to see equations. Equations are way easier to get marks because you write less. Okay, okay, let me just edit the answer here. Okay, this question only asks for OH minus, so you just need to write one equation. Okay, when you add a small amount of base, NH4 plus will react with it. Full arrow, remember it's neutralization, must be full arrow. Okay, so then you tell me small amounts of OH minus added is completely removed by the large excess of NH4 plus. Or you can even write NH3 inside also. In this case, we will write NH3. Okay, so it's by a large excess of NH4 plus pH remains relatively constant. Okay, alright. Okay, almost done for today already. We will do a few calculations and then we are pretty much done. Right? Okay, so what we have gone through so far is the tech. Okay, it's just how it works, right? Okay, how does buffer work? Uses neutralization because it contains a conjugate acid base pair. Okay, that's all we have learned so far. Now we're going to look at the calculations. How does the calculation work? Okay, so not much. Just going to introduce an equation that you should memorize. Okay, take a look at page 34. Now, I'm going to explain what the first bullet point means. Just now you guys may be asking, right? If let's say I have both NH3 and NH4 plus in the same mixture, some of you all may be asking, right? What if the NH3 weak base dissociates into OH minus? Right, and then you will like change the buffer's pH and all that. Okay, some of you all may think about that, right? Okay, but it doesn't happen. Why? Based on the first point, right? This is what they're trying to say. Now imagine this, okay, I have NH3 if it tries to dissociate into NH4 plus, this would have been the equation, right? Okay. You leave NH3 alone, there's a chance it can produce its own OH minus. Then people will be asking, then wouldn't it dissociate into a lot of NH4 plus? The reason why this doesn't happen, there's no dissociation. It's because you can ask yourself, NH3 and NH4 plus, are they a lot or very little? A lot. Now, if there's a lot of NH3, the position of equilibrium will be forced to the right, right? But can you see there's also a lot of NH4 plus? So can you see they are battling each other? This one will force it to the right, this one will force it to the left. So at the end of the day, does it go anywhere? No. Okay, so in other words, this is what it's trying to say. Because NH3 and NH4 plus are in very large excess, it means that it will suppress the dissociation. And this makes our life infinitely easier, which means our buffer, you only need to bother about neutralization. Now the other shit involved. Okay, so let's not lump anything else together. Okay, so if I put NH3 and NH4 plus in the same container, in the same buffer mixture, they're just gonna sit there, literally sit there. They won't do anything. It won't react by itself to produce OH minus or whatever nonsense. It just sits there. Okay? Can? It's like they try to tussle it out, right? And then no one wins. Right? Okay, write this first, I'm gonna erase it. Okay, the equations you see at the bottom of that page, okay, go and memorize that also. Okay, it's way better, it's just way better. Okay, you don't need to memorize actually. If you know the K expression, you can calculate it. But I suggest you memorize. Okay, why? Now, this equation that we have, right, is called the Henderson equation. So whenever, guys, I say the word Henderson equation, it's only for buffers. Don't use this for anything else. Okay, only for buffers. Now, if you are given pKa, then you use the first version. So pH plus pKa, pH equals to pKa plus log. Now, how do you remember this last part? This last part, a lot of people tend to forget. A stands for acid, right? Just try to memorize this in this way. The acid will be at the bottom. Okay, on the other hand, POH is accompanied by PKB, right? P stands for base. The base will be a bit at the bottom. Okay, yeah, this part here, a lot of people tend to mix up. So I need you to be careful. Okay, so this is how you should memorize this. A for acid, the acid is at the bottom. B for base, base at the bottom. So you highlight it like this, color code it or whatever. Okay, if the acid is at the bottom, then what's on top? It must be accompanied by its partner, right? Which is the what? Conjugate base. Okay, now they are related, so you use the word conjugate. Okay, so PKB, the base at the bottom, who's on top? Conjugate acid. Okay, use this way to memorize. I realize it's the most flexible way after I've tried multiple iterations over the past few years. Okay, this is the most reliable. Okay, later you see there will be confusions. Okay, so I think this will avoid that confusion. Now, take a look at page 35. Okay, these equations will help to speed things up massively. So, page 35, that question over there, right, is literally to ask us to calculate, this is the first version, calculate the pH of a buffer. Now, how do you know that there's a buffer in the first place? Okay, we just scan through this question. How do you know that there's a buffer? Can you tell me? Because they just say calculate the pH of a solution. Okay, how do I know there's a buffer? Exactly, right? A buffer must contain a conjugate acid-base pair. And I have literally those two. That's how I know it's a buffer. So you must identify the question type first. Don't tell me suddenly got one salt hydrolysis come out. How does that make sense, right? Okay, you must know what you're getting into. Okay, guys, the values are all given now. I just need you to substitute values inside. Pretty sure you can do it. Okay, use the whatever equation that's appropriate to you guys. Okay. It is not the important question anyway. The next question then is more important. Okay. Yeah, you should know what the acid and the conjugate base is in this context, right? Negative log. Okay, whenever you all see the P, just put a negative log there. Okay, then plus log. Right? Okay, look at the working very carefully. I know both of the species are the same, but I need you all to divide by one. I know spoilers, they'll cancel each other out, but you all know why? The formula is in concentration. The values they've given you is in moles. It's a small little thing. I know the answer is still the same, but I don't know how strict and anal your teachers can be, so let's just be safe here. Okay? Your final answer here should be 4.74. Because log 1 is equal to 0, so that one doesn't actually count. Okay, I need you all to know what you're doing for this question first, so you understand the difference between this and the next question. Here, I am calculating the pH of a buffer. That's it. I have two species sitting there, doing nothing. You just calculate the pH. That's it. Okay, can? But now, we're going to look at the next version. The next version is a little bit different. Right here. Look at the title of this next part. I need you to highlight change in pH, bottom of page 25. It's a more tricky iteration here. Calculate the change in pH of a buffer, not just the pH. This version, variation of the question, right? You must understand what they are doing first. Guys, how do you change the pH of a buffer? What do you do to it? Okay, you want to change a bit also, just add small amounts. Okay, if you add a lot, right, it won't become a buffer anymore. Okay, but I get what you're trying to say here again, no? You want to change the pH of a buffer, right? Just by a bit, so just add small. Okay, so you should know what you're getting into. There is already a buffer here. They want you to calculate change when you add H plus. Are you adding anything here in the first variation? No. They just have the acid conjugate base you just calculate, but here there has some changes on. Okay, how does it look like? Okay, you can skip the steps because I'll tell you guys anyway. Page 36, read through this question first. I want you guys to later see the part, right, that actually tells you there's a change in it. Okay, but just read the whole thing first. Let's do this question together. Okay, I'm going to go through the steps. The first variation was a bit too easy. You'll just plug and paste values. Probably you can get 1 mark if they're nice. Okay, but sometimes if they're not nice, they won't even test that. Okay, they'll give you this scenario. Okay, so you'll notice the first paragraph of page 36 is just to tell you the buffer initially. Agree? They just show you the buffer, nothing, okay, that is peaceful. And then they go and add some HCl to the buffer. Okay, what will happen to the pH? It started off at 4.74. What will happen afterwards? It'll be lower, right? By a lot or very little? Okay, very little. Okay, so how? First step, I need you all to come up with a neutralization equation. I'm sure you all know what is neutralization. Because buffer uses neutralization to remove H plus. Come up with that first. And then afterwards, just at the same time, do an ICF table, not E, because it's not a equilibrium. Neutralization is 2 arrows, as I mentioned. So it's F. But after you do all that, okay, later we'll go through together. Then to find pH, you plug it into the Henderson equation. Okay, Henderson is only for buffers. Okay, equation first. Table, you can try also lah. Okay, equation and table. Then we'll go through. Okay, equation first. They add HCl. Whose job is it to remove the HCl? Good, the base, right? Okay, so don't write HCl, just write H plus, settle already. What do you get? What arrow, sorry? Full. It's a neutralization equation. Okay, next. ICF table. Okay, this table I need to clarify what to fill in. What's the initial amounts of acid and conjugate base? They tell you, right? Okay, remember this table, let's do it in moles. ICF table in moles. If you do it in concentration, I can tell you it's never a good idea. It's never a good idea to do it in concentration because here you are adding shit. You're adding things inside, right? The volume is going to change and then later the concentration not accurate. Why do all that to yourself? Okay, do moles. Okay, remember, we are just adding stuff to an existing buffer, meaning the initial amounts of the buffer must contain both acid and conjugate base. Don't just say the right hand side is 0. No. Here, there's already something inside. Can? Okay, guys, what's the initial amount of H plus? What should I put here? 0.00. Yes, okay, correct. Now, I know some of you all see just H plus, then you go put 0 here. No. Okay, it is 0.001. It's how much you are about to add inside. Okay, so to interpret this, right, this box here, you can write down. It's how much HCl I'm prepared to add inside. I haven't add yet, but I'm prepared to add. But then guys, can you tell me what's the change? What's the change? So this is the limiting reagent, right? So you must minus 0.001. This is where you actually add inside already. And then it reacts. So the change is the reaction. Okay? This is where HCl actually reacts. I need to clear up this confusion. Because if not, people will give me a lot of weird iterations of the table. I don't know how to. Okay, so go at minus 0.001 on the left, plus on the right. As you can see, the proportions of the acid and conjugate base are slightly different. Now notice that I still have acid and conjugate base, right? Okay, acid and conjugate base. I will still form a buffer, right? But now I need you all to perform the calculations, Henderson equation. That's the last step. The pH is not going to be the same because you have to get the proportions of both acid and conjugate base is slightly different. Let me calculate that now, right? So I'm going to find the final pH, the new pH. Okay, do your pH equals to pKa. They've already given your Ka value, so just put a negative log there. Plus log. Remember the acid. You're using pKa, so acid must be at the bottom. Okay, so acid here is CH3CO2 0.011. Base on top, conjugate base on top, 0.009. But I need you guys to divide by the volume. You can see that? Okay, this is in moles. Okay, so I need to see this change to volume. The volume here, right? Don't bother calculating from now on. Okay, just like divide by. It's just to show you're working. They will always cancel each other out because they are in the same freaking container, right? Okay, so they will never ever cancel. They will never ever be different. That's what I'm trying to say. Okay, but just show that you're converting, you're making the effort to change it to concentration. Your final pH here should be lower at 4.66. Can? But they want to change in pH. So guys, how do you find the change? Okay, now just follow final minus initial. There's a decrease in pH, so there is a negative value, 0.08 pH. If pH no units, so just put 0.08 negative there. Okay, let me address that actually. Someone asked about that also. Okay, if you're trying to calculate using the second formula, it will still get the final answer. You will still get a pH of 4.66. Like, if you don't believe, you can write this other variation down now. If you want to find pOH, right here, let's say the question gave you pKb. Okay, let's say they did. You can switch it to Ka and use the first formula. Can. But if you don't want to switch, it's actually possible also, but I suggest to switch. Okay, if you don't switch, okay, the Kb in this case will be, if they will give you this 5.56 times 10 to the power minus 10. For those who want to switch to Ka, you'll get back this. Then the answer will still be the same. Okay, but I want to go through the second part, this part, the ratio. Plus log, what's at the bottom, guys? Use Kb, what's the base at the bottom? The base. Okay, ask yourself, guys, what is the base in this question? CHBCO2 minus, it will be 0.009 at the bottom, 0.011 at the top, correct? If you're going to calculate out pOH, can just someone faster calculate this out? Okay, just tell me the answer. It's to prove the point out. You can use both equations to still get the correct answer. It's all linked. pH and pOH is linked, pKa and pKb is linked. You will be safe as long as you know who's on top and who's below. You will be safe. Okay, so I don't know what the answer is here. What is it? Should be 8 point something. No, wait, 9. Okay, 9.34. 9.34. Okay, guys, but this is pOH, right? You switch back to pH, how? 14 minus 9.34 or 4.66. Still get answer. Okay, so depending on what the question gives you, right, you are quite versatile. And that's it for me. Okay, so next week we're going to continue a bit more on buffers. We haven't finished buffers yet. Some small little concepts. Please review this lesson before you come for the next lesson. So maybe one day before the lesson, like Saturday or something, or whatever lah. Okay, find some time, look at what we did today, so next lesson won't die. Okay. Then next lesson we finish up the topic. Will still be quite intense.